So pretty much everything we do in Chapter 4 leads up to the concept of trying to use calculus to find out the conditions under which certain things are as big as possible or as small as possible. So for example, if you were, and I'm getting way ahead of myself, but we might as well talk a little bit about it. If I were designing a soup can, and the soup can had to be designed so that it was going to hold 1 liter of soup, big soup can, as soup cans go. What I could do, I suppose, is I could make a can that was about this big across and just have a little thin layer of the can. So a very, very short height and a very, very large radius. But as a manufacturer and a business person, I'd be throwing my money away because that's wasting the materials to produce the can. On the other hand, I could think, well, maybe if I make the radius really, really small, like a centimeter for the radius, that will save me money in materials, but it won't because then the can is incredibly tall. And somewhere in between, there's this optimal set of dimensions. Optimal means perfect for our needs, and that's going to produce a minimum cost. And we're going to use calculus to solve these kinds of problems. But today we're going to start off by just looking at what it means to talk about an increasing function and a decreasing function. And we're going to be determining where functions increase and where functions decrease using the derivative. So we're going to be investigating where functions have values that we say increase over x. And I'll officially show you what that means in a second, but verbally what it means is as x increases, as we go from left to right on a graph, is the function increasing or decreasing? That's what we're talking about. When we speak of a function increasing or decreasing, and this is what I just said, we're talking about left to right. So if I say a function is increasing over the interval x equals 1 to 5, that means when you look at the graph of the function from x equals 1 to x equals 5, the slope will be positive. The function will be going up. There are multiple ways in which you can answer this problem, namely where is a function increasing or where is it decreasing, but I think I've kind of led up to it already by saying if the function is increasing, the slope is positive. And since we're a little more sophisticated than just talking about slope, we talk about the derivative of a function. If the derivative of a function is positive on an interval or over an interval, then the function is increasing. If the derivative of the function is negative, then the function is decreasing. So this is what we're talking about. Just take a second and read that statement. I've already verbally given it to you in one way or another, but just read it and think about it for a second. Positive slopes mean the graph is going up from left to right. Conversely, or similarly, wherever the derivative of the function is negative, you can follow that same logic and say the slope must be negative in that region. I'm not implying or suggesting that the slope is some negative value and it's a uniform slope everywhere. I'm saying that in that interval, everywhere the slope is negative. And in order to answer where functions are increasing or decreasing, we use what's called a first derivative chart. There are other things called the first derivative test, which is not quite the same as this. So this is going to be a first derivative chart that we'll get to in a bit. But here's a cubic polynomial function. Even if you're in Math 30-1 right now, you've learned about polynomial functions. This is an odd polynomial function that increases forever and decreases forever. And the reason I mention that is in this context box, there's this phrase local maximum and local minimum. And the word local is used purposefully. See, this point right here, maybe I will use a different color. This point right here is a local maximum. And this point at x equals -3 is a local minimum. Without the word local, if I just said that yellow point is a maximum, that would be a mistake. because the word maximum means it doesn't get any bigger than that. And when we're talking about maximum and minimum, you should know this from other courses, we're talking about the vertical maximum and vertical minimum. We're talking about the maximum function, and function is y. So this yellow point is not a maximum value of the function, but it is in that vicinity a maximum value. Sometimes instead of local maximum, we call it approximate maximum. And there are other words that we can use. We're a little more picky, and I don't like this, but in Math 30-1, and those of you in it right now should remember this because we've talked about it recently. When you see the word maximum in Math 30-1, you're talking about it's the maximum. It's not bigger anywhere else. In calculus, we like to just cover our bases and call those maxima an absolute maximum. So there's a difference between an absolute maximum and a local maximum. Similarly, this blue point is a local minimum because in the vicinity of this region, it's the lowest point. Okay. So that's the graph we're looking at. What are we asked to do? Determine the domain in which the polynomial function is increasing. So what we are interested in is looking left to right. What is the domain of values of x that describe where the graph is increasing, where the graph is rising? And you don't necessarily have to add this to your diagram. I'm just going to point out that the graph is decreasing in this region. And I'm making the arrows shorter and shorter because it's not decreasing as rapidly as I get closer to that point. And after I pass that point, which is a minimum, what happens is the function starts increasing. And it increases rather rapidly, but then the rate at which it increases kind of tapers off, and it reaches that maximum. And then, of course, what happens after that is it's decreasing, and it's going to get steeper and steeper to infinity. And these arrows on the left-hand side could also be continued towards negative infinity. So where is the function increasing? The function is increasing, and I'm just in a teaching mode right now. The function is increasing not here and not here, but it's increasing everywhere in between. And I say I'm just in teaching mode. I said that because I don't think you need to draw this on your graph. You're just in learning mode here. You're saying, where is the function increasing? It's increasing. I wonder if this will work. I suppose it will. I'll just have to use a thin line. It is not increasing here. It is not increasing here, but it is increasing everywhere there. I had to put that line because otherwise my program just connects the 2 points, the 2 endpoints with a straight line. So what's the domain? What is the answer to this question? F of x is increasing. We say on. You can say over, but very often we say on the interval -3 is less than x, which is less than 1. Does that make sense to you? I don't think we need to redraw all of these arrows to answer the next part of the question, which is, what is the domain in which the polynomial function is decreasing? It's decreasing everywhere from negative infinity up to, but not including, 3, -3. And it's also decreasing after positive 1. So when we look at the next part of this question, determine the domain in which the polynomial function is decreasing, f of x. And, we're not going to be that picky here. You could say, well, Mr. Way, isn't it p of x? I realize that now, but you get my drift. Okay? The function p of x or f of x is decreasing on negative infinity. Wow, geez, we could do this. And very often we get used to doing that, and we forget that there's a much cleaner way of saying that. x is less than negative 3, right? You could just say x is less than negative 3. I don't think that's an issue, though. And on x is greater than positive 1, or 1 is less than x, which is less than positive infinity. I don't care how you write it. You can use interval notation. You can use the fancy set notation. It doesn't matter to me. Any questions with 2? Okay, 3. What is the domain in which the polynomial function is neither increasing nor decreasing? And this goes back to these arrows I drew, that I didn't draw an arrow up or down at negative 3 or up or down at positive 1. Because we'll pick on 1, at 1, the function is increasing to the right, increasing to the left of 1 and decreasing after. It is not increasing or decreasing at 1. And you can think of this as maybe being the path followed by a ball thrown in the air. Before it reaches that vertex of its motion or apex of its motion, the ball is rising. It's getting further away from the ground. And immediately after, it's getting closer to the ground. But at that instant in time, it's neither rising nor falling, which is why if you throw a ball straight up in the air, at that top point, its velocity for an instant is 0. Okay? So the answer to this question is f of x, and I want to be very picky on how we write this. F of x is neither increasing nor decreasing at x equals negative 3 and x equals positive 1. And although we're not going to encounter this right away today, but I believe one of the examples will illustrate it. I know there's probably a desire by some of you to just say, and we still have to relate this to the derivative. Let me back up and do that first. We were asked to relate where the function is increasing to the derivative. And we said the function was increasing on this interval. That means that dy dx, whatever notation you want to use, if you want to use p prime of x or f prime of x, I don't care, is greater than 0 on negative 3 to 1. I hope you agree, and I still have this green streak up here, which is the domain we're talking about for question 1. I hope you'd agree that the slope everywhere there is positive. And we're not including at the minimum or the maximum. Similarly, we could do the same thing here, that dy dx, the derivative of the function with respect to x, will be negative on, I'm just going to use a different notation here, on the interval from negative infinity to negative 3, not including negative 3. And of course, not including negative infinity, because you can't. You'll never get there. And also on the interval from 1 to infinity, but of course not including 1. Now, I'm being overly picky here. Maybe I'll start with the statement about the derivative for question 3. The derivative is equal to 0 at x equals negative 3 and x equals positive 1. And some of you are going to come to the conclusion very quickly, and it's somewhat valid. Depends on how you say it. Here's the proper, correct statement. There's no flaw in it. Since the derivative is 0 at that point, and the function is defined to the left and the right, those points must be maxima or minima. I mean, just roll that around in your head. If the slope of the tangent, which is the derivative, is 0 at a point, and the function is, well, that's even not correct. We're going to run into situations where that's not correct. Let me be even more specific. If the derivative of the function is 0, and to the left of that point, the function is increasing, and to the right it's decreasing, then that point must be a maximum. Does that make sense? So if you look at this region of the graph, the slope of the tangent at this point will be 0. The derivative at that point is 0. The derivative is positive to the left and negative to the right, so that point must be a maximum. Similarly, the derivative of the function at that point, at -1, is 0, and the derivative is negative before and positive after, so it's decreasing then increasing, and it's defined everywhere with a slope of 0 at that point. That's a minimum. But I want to, and I don't want to go down this rabbit hole too deep today, I want to point out that there's a number of weird things that can happen. Just because the derivative is 0 doesn't mean it's a maximum or a minimum. How can you have, just briefly to help you out later in further lessons, how is it you can have a slope of 0 but not have a maximum or a minimum? The answer is you have some kind of inflection point where the tangent slope happens to be 0 at some point, but because the function is increasing before and increasing after, that doesn't count as an extreme point. I will give you, so here, dy dx equals 0, but it's not an extreme point. It's not a max or a min. Then again, and I'm talking here about all of the possibilities, it's going to get complicated, I can have a maximum or minimum and the derivative is not 0. Let me repeat that. I can have a maximum point on a graph, but the derivative at that point is not 0. Does anybody know how that can happen? And keep in mind, today, all we're focused on is finding increasing and decreasing. I'm just embellishing what we're learning now to further ideas. The answer is if you have this kind of a point, which is called a cusp, that is a maximum. But the derivative there is not 0 because the derivative there is not defined. And it's not defined because the derivative is a slope of a secant line taken as a limit. And the left-hand slope and the right-hand slope are not equal. They're not approaching the same thing. So the limit doesn't exist, so the derivative doesn't exist. So I wanted to spend a few minutes talking about that. I think you understand the gist of questions 1, 2, and 3. But I don't want you to draw any invalid conclusions. I don't want you to build some misconceptions on this. All we're doing is where is it increasing, where is it decreasing? And it happens to be, well, the connection between where it's increasing and the derivative is always true. If a function is increasing, the derivative is positive. If a function is decreasing, the derivative is always negative. If it's neither increasing nor decreasing, it might or it might not be a maximum or minimum. But in this case, the derivative is 0. All right. I'm going to add something here, and I don't know if you want to add it to your graph or not. But it will be useful in Chapter 5, where we do the following. I'll use, since I've already committed myself to f of x instead of p of x, I'm going to use f of x and f prime of x. And the idea is that there is this point here. It's a critical point for x because some things change. The derivative changes and what the function is doing changes. And there's also a point here where things change. And what's happening is the function prior to this point is decreasing, and then it's increasing, and then it's decreasing. And what that means is the derivative is negative, then positive, then negative. And by the way, we could draw another section on that for the second derivative, but we won't learn about that for at least a week or so. What's happening at these critical points, I will tell you this. If the derivative goes from positive to negative, goes from this to this, then where it changes might be a maximum. And where the derivative goes from negative to positive, that might be a minimum, but it might not. All right. To determine algebraically the intervals without looking at a graph, that's what I mean by algebraically, we do a first derivative chart. And every example we do today, we're doing 4 of them. We're just doing a first derivative chart to learn where the function is increasing and where it's decreasing. I might, along the way, talk about maxima and minima, or I might not. We'll see. So the first step, think of this logically. If you want to find out where a function is increasing, then you need to know where the derivative is positive. So you have to find the derivative. Couldn't get much easier than this. I'm going to switch to the dy dx notation. dy dx equals negative 5 minus 14x. So think about what we're asked to do here. We're asked to determine where the function is increasing and where it's decreasing, which means we're asked where is the derivative positive and where is the derivative negative. Well, logically speaking, before you find out where it's positive and where it's negative, you have to find out where it's neither. You have to find out where, in this case, it's equal to 0. So where is the derivative equal to 0? That's really simple. You set that equal to 0. It's a linear derivative. You know, I would say you should factor it, but there's nothing to factor out. I suppose you could factor out the negative, but it doesn't really matter. You know, I would say that everybody here should be able to determine that it's negative 5/14. And, you know, if you want to, I would really resist the temptation to do that, because you've just told me dy dx is equal to 0. You told me the derivative of the function is 0. And it's not. If you're going to do that, then you do this. Negative 5 minus 14x equals 0. And you solve that and get negative 5/14. Correct? Okay. So when you look at this function, and my explanation here is maybe overkill, but when you look at that function, you know from previous math classes that's a parabola or a polynomial function, and it's defined over all real numbers. And what we're reasoning out by saying that at x equals 5, negative 5/14, at negative 5/14 the derivative is 0, that means everywhere else it's not 0. So we did this, by the way, in the questions in the lesson dealing with position, velocity, and acceleration. If this is where the derivative is 0, then to the left of it, the derivative must be positive or negative everywhere. And to the right, it must be positive or negative everywhere. And I want to go through that reasoning again. It's not possible for the derivative of this function to be positive here and then negative. We'll just even go that far. It's not possible for that to happen, because then you're saying the derivative changes from being positive to negative, which means it has to pass through a value of 0, because this is a continuous function. And there is no value of 0 there. So how we determine where the derivative is positive and where it's negative is we write out a first derivative chart which shows the domains that negative 5/4 create when it slices the domain of all real numbers. So we're looking from negative infinity to negative 5/14, from negative 5/14 to positive infinity. And across the top, we would put all of the factors of the derivative, but there's only one factor of the derivative. It's negative 5 minus 14x. So this is the derivative. I'm going to add a second column anyway, and I'll get to that in a second. And what you need to do is fill in, you remember doing this with position and velocity, positives and negatives? You need to put positives and negatives there. How many of you remember me telling you that the linear factors go from negative to positive as they pass through the zero? Does anybody remember that? Okay. Well, it doesn't always happen. It will happen if the coefficient of your x term is positive. So do me a favor. Take a number, any number you want, and you don't even necessarily have to calculate it. You can think about what's going to happen. Like negative 10 million. And ask yourself what this factor is going to be when you put in a number for x, like negative 10 million. Well, you're going to get negative 14 times negative 10 million, which is an incredibly large positive number. Plus that negative 5, it goes from being positive to negative. I just want to look at something. Good. I thought I had a little scare there because I thought maybe I did something wrong, but I'll tell you what my thought was in a minute. So, I know it has to change here. But go ahead and put in a number that's in this second interval for x into negative 5 minus 14x. And make sure you convince yourself that you're going to get a negative. So what does that mean? It means that dy dx, and I have to add another column. It means that dy dx is positive in this interval and negative in this interval. And what is that telling us? It's telling you y is increasing then decreasing. Which, you could have figured out by just looking at the fact that it's a parabola that opens down. Okay? But, and I don't want to get too far away from what we're learning here, but this negative 5/14, if that's where the derivative is 0, that's the x-coordinate of the vertex of the parabola. And in Math 20-1, you would find the vertex by completing the square. No need. So the answer to the question is the interval of increase is here, the interval of decrease is there. I can write that out if you like. The function is, I'm going to abbreviate a couple things here, increasing on negative infinity, negative 5/14, and the function is decreasing on negative 5/14, positive infinity. The mild scare I had was I know when I look at this increasing then decreasing, this is a parabola that opens down. All right, think about it. If it's increasing then decreasing left to right, it must do that. And I thought I saw a positive x squared up here. I really did, and that's why I went, oh, geez, really messed that up. And then I scrolled up and went, nope, it is a negative x squared. Any questions with the first example? All right, cubic polynomial function. The first step is to find the derivative. I don't like prime notation, but I'll go with it. 3t squared minus 24t plus 36. Why are we finding the derivative? So we can find out where it's positive or negative. How do I find out where it's positive or negative? I start by finding out where it's 0. I never write, there's going to be exceptions, but I don't want to get in the habit of writing the derivative equals 0. You find out where a derivative is 0 by looking at it in factored form. We've been doing that ever since you learned about all of the algebra we've been doing with limits or anything else. It's always been about putting stuff in factored form. I believe that's factored correctly so far. which means the derivative s prime of t is 3 times t minus 2 times t minus 6. What we are doing is we're finding out where it's 0 by never actually saying dy dx equals 0. It's equal to 0 at 2 and 6. So again, what this means is at 2 it's equal to 0, at 6 it's equal to 0. The big question is, what is it here, what is it here, and what is it here? Because the derivative has to be positive or negative here. If we know it's positive here, then we know the function is increasing there. And we've answered part of the question. So we make a chart. The first derivative chart, and I say that because we do second derivative charts later, will be from negative infinity. These should be in order. They don't have to be, but logically speaking, it makes more sense and it's easier to follow. From negative infinity to 2, from 2 to 6, and from 6 to infinity. And our factors across the top, they don't have to be in any particular order. And I really want to slow things down here. Well, let's finish the bare bones of this. This will be s prime of t, which will tell us something about s of t, which is what the question is asking about. And the functions get a lot more complicated than just quadratic or cubic. I hope everybody agrees that since these three domains are all, there's a word that's escaping me, they all have round brackets. They don't include the endpoints, right? That we would never use t equals 2. And we would never use t equals 6, right? But I want to point out that t equals 2 is the 0 of t minus 2. Think about that just for a second. Two is the 0 of t minus 2. So if I graph y equals t minus 2, that's a linear function with a slope of 1 that passes through 2 on the x-axis, because that's the 0 of t minus 2. And I'm pointing out that since it's linear, to the left of 2 it's negative and to the right it's positive. Which means we don't have to think very long or hard about what these signs are. You can certainly put numbers in and figure it out. But if 2 is the 0, then t minus 2 must switch signs as it passes 2. Similarly, t minus 6 will be negative everywhere to the left of 6, and then it will become positive. Do you remember me saying a minute ago something about the rule not working because it was negative 14t or negative 14x? If the coefficients of your linear terms are positive, that means, graphically speaking, they represent lines that increase, so they go from negative to positive. And they will switch as you pass the 0. What does that mean? It means the derivative is positive because it's the product of these two things. So in this interval from negative infinity to 2, the derivative is always positive. Then it's negative because positive times negative is negative. Then it's positive, which means the function is increasing, then decreasing, then increasing. And we've answered the question. At some point during this lesson, I'll probably say, I'm not going to write it every time, but I'm going to write it again this time. S of t is increasing on negative infinity, comma 2 in union with 6, comma infinity. And S of t is decreasing on 2, comma 6. by the way, there's a lot of background that goes into this conclusion, but it's valid. There must be a maximum at x equals 2 or t equals 2. It's a cubic polynomial function, which is a continuous polynomial function. The leading coefficient is positive. From Math 30, you know the right arm is up. Since it's cubic and odd, the left arm is down. Well, you've just determined how to determine the maximum of the function. We haven't actually found the maximum. You would have to put 2 in for t into the function and see what you get for y. So you Math 30-1 people, that folding cardboard creating a box thing where you have to find the maximum value of that cubic function, that's how you would do it algebraically. You'd take the derivative of the cubic function, set it equal to 0, and go from there. And by the way, this would be where t is equal to 6. Again, it's not necessary that you know that for today, but we're going to build on this and add those layers later. Any questions with B? All right? Why not? Degree 4. So the first thing we have to do to find out where it's increasing or decreasing is find the derivative, because if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. All right. 4x cubed minus 12x squared minus 16x. Good. I'm avoiding the use, I believe, of the quadratic formula. If there was an x term in there, then we would have a lot more work to do because we'd probably be using the factor theorem to continue. Can you confirm my derivative is correct? I'm pretty sure it is, but okay. So factor, always factor. I can take a 4x out of the derivative. Sometimes I don't like that phrase, take it out. It's not like you're removing it. It's still there. You're just writing it elsewhere. And then we have x squared minus 3x minus 4, which factors. I want to go back to the previous example. Man, I really meant to make this point and I didn't, and I think it's important. When I built my chart, look at what I have here. It's not a mess up, it's just something that I don't want you to get in the habit of doing. So it's going to be do as I say, not as I do. That's not the derivative. There's the 3 there, isn't there? So what we should be doing is including the 3. And if you like, and this is what I would prefer, you just include the 3 with the t minus 2, and then you don't have an extra column. What your textbook does in places, and it's not wrong, I just don't like it. What your textbook does in places is it adds another column for that constant. And I do like doing that if that constant's negative. But we should be putting that there. And the reason why I was reminded to go back and do that is when we make our chart here, 4x is a factor. It has to be included. Even if there's no x there, you should include that 4. It's part of the derivative. And then across the top, we also have x minus 4 and x plus 1. And what are our zeros of the derivative? I'm going to start calling them from now on critical numbers of x for the derivative. They're critical values of x because the function changes its behavior there. And the derivative changes there. I shouldn't say the derivative changes there. What I should say is the derivative has a unique value there. 0, or it turns out undefined. Hope everybody would agree those are the 3 zeros. So we imagine taking the line from negative infinity to infinity, and we take a mathematical knife, and we slice it at x equals 0, and we slice it at x equals negative 1, and at x equals 4. Creating the following subdomains: negative infinity to -1, -1 to 0, 0 to 4, 4 to infinity. If I have a foot-long sub and I make 3 cuts, I'm going to have 4 pieces. So, again, you do not have to do it this way. I'm just pointing out that there are shortcuts available. That the -1 occurs between these two intervals, so the x plus 1 will switch signs as it passes that 0. It will be negative before and positive after. Since 0, which is the 0 of 4x, occurs between these two intervals, 4x will flip as we pass that 0. And it takes the, I got to pick a number, I got to put a number in, see if it's positive or negative. It takes that clunky business out of the mix. And this will switch from being negative to positive as it passes 4. So g prime of x will be negative. I'm using a different color, but it's a good idea in your notes to circle it, to differentiate it from, bad word, to distinguish it from those other positives and negatives to the left. So I'm just multiplying the 3 negatives to get a negative. Here I will get a positive, here I will get a negative, here I will get a positive. And by the way, they don't always flip back and forth necessarily. You can get negative, positive, 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 negative, positive. Depends on the function. What is that telling us about g of x, which is the question? G of x is decreasing on these two intervals. I'm not going to write that out. If you wanted to write out officially an answer, g of x is decreasing in the interval negative infinity to -1 and in the interval 0 to 4. Are you picking up what I'm saying here? You're getting this? Okay. And then it's increasing here and here because the derivative is positive. And by the way, looking ahead, this is a degree 4 polynomial function, which is a continuous function over all real numbers. This must be a min. This must be a max. This must be a min. So now you know how to find out the maximum and minimum locations for a degree 4 polynomial function. And presumably you could do it for any polynomial function. I better be careful here. In other courses, I'm not too concerned about this kind of language, but when I say min and I have an arrow, I'm not saying the minimum is -1. The minimum is f of -1. You have to put -1 into the function. So to finish this off, let's take a look at a function that is not polynomial. And one of the first things you always, well, not one of the first things. The first thing you always need to look at, and we didn't need to in the previous examples, is what's the domain. Because the last thing we want to do is start slicing the domain of all real numbers into pieces if the function doesn't exist in parts of those places. Because if the function doesn't exist and you build your table, including those domains, you're going to get confused. So we do have a domain restriction on this, that the radicand must be greater than or equal to 0, which means we've had this discussion. I've taught all of you, or I'm currently teaching all of you. We've had this discussion in Math 20-1 and 30-1. I choose to rearrange an inequality where the x is negative by moving the x to the other side and then reading it right to left. So if 9 is greater than or equal to x, then I know x is less than or equal to 9, which makes sense. Look up there. If you had an x value that was not smaller than or equal to 9, if you had x equals 10, you're going to end up taking the square root of a negative, which is not allowed. So our domain, I don't want to do that. Our domain is from here to infinity. There's nothing to the left of the 9. So now we have to find the derivative. I think most of you have grown to the point where you don't need necessarily to write that to know that it's a 1/2 and to differentiate it using the power rule as part of the product rule. But I'm writing it up there. Derivative of the first times the second plus the first times the derivative of the second and you know, I'm sure you can imagine why, but if your derivative's wrong, then your chart will not make any sense when you try to piece it together as a visual graph. And this derivative is not complete until I multiply by -1, which is the derivative of what's inside. And just that negative, I mean, you can take the standpoint that if it's wrong, obviously. But when a derivative is wrong, everything else just gets really confusing afterwards because you're trying to build something on an incorrect starting point. So what do we do here? Well, let me just clean it up a little bit. I'm going to write this as 9 minus x to the half minus x over 2 times 9 minus x to the -1/2. And we are going to want to know, does that look okay, you guys? Okay, we are going to want to know where this is 0. We're also going to want to know something else, and I'll reveal that in a second. But you cannot necessarily look at that. I know some of you can. But you cannot necessarily look at that and tell me the values of x that make it 0. And if you can, you won't always be able to. There's something else we need to know, which is what are the values of x that make it undefined, and I'll explain why in a second.
Thank you.
You cannot necessarily look at this and tell me where this derivative is 0 and where it's undefined unless it's in factored, cleaned up form. So the first thing I'm going to do is I'm going to multiply the top and the bottom of this by 2 to get rid of the 2 on the bottom of the second term of the top. We've done this before. You've seen this before. So you get dy dx is equal to 2 times 9 minus x to the half minus x times 9 minus x to the half over 2. So I multiply the first term by 2. I multiply the second term by 2, which cancels the 2 under the x, and I multiply the bottom by 2. Now I'm going to factor out, this is a -1/2 on the 9 minus x in the second term. Now I'm going to factor out that 9 minus x to the -1/2. And I will have 2 times 9 minus x minus x. And I'm going to double check that in a second because total autopilot in my head right now. So I take the 9 minus x to the -1/2 out of 9 minus x to the +1/2. I get 9 minus x to the 1. To me, it looks okay. We're on the same page here then? Okay. So that means I get dy dx is equal to 18 minus 3x, just double check my little bit of algebra there, over 2, 9 minus x to the half. And just to go one step further, dy dx equals 3, 6 minus x, 2, 9 minus x to the half. So I've been very thoughtful in how I've introduced certain words. I'm no longer talking about where the derivative is equal to 0. I'm talking about the critical values of x. And there's no easy way to do this. The lessons, the next 3 lessons all kind of weave together around the same idea. A critical value of x is where the derivative goes from positive to negative. Okay, and I want to go back and take a look at a couple of situations where the derivative went from positive to negative or from negative to positive. Would you agree the derivative, I'll go to the original graph, would you agree that x equals negative 3 is a critical value of x because the derivative goes from being negative to positive? And 1 is a critical value of x because the derivative goes from positive to negative. And that's kind of centralized around the fact that those points are where maxes are. But would you agree here the derivative goes from being positive to negative? It's going up and then it's going down. That is a critical value of x, but it's not because the derivative is 0, it's because the derivative is undefined. So from now on, whenever we're dealing with finding critical values of x for a derivative, it's where the derivative is not defined and where it's 0. Where is it 0? You eyeball the top of the derivative. Where is the derivative undefined? You eyeball the bottom of the derivative. And it's all about factors. If the top and the bottom are not in factored form, you can't just look at it and say, oh, x equals 9. So we have two critical values of x, 6 and 9. So what will our chart look like? Our chart will go from negative infinity to 6. Correct? And then what? Well, then 6 to 9. And then what? Is there another interval?
9 to infinity.
No, because the domain, and I sucked you into that, because the domain is x is less than or equal to 9. And you would find, if you put 9 to infinity here, everybody, you'd find that you'd start filling in blanks and going, wait a minute, what the heck is going on here? It wouldn't make sense because you'd have square roots of negatives. So this is the thing, though, the tough part. You start with this, and then you go through this big slog of work, and you get to the bottom, and you've probably forgotten what you were doing. Right? So you have to look at the original function and its domain. So that's it. And I want to bring this all to a close after we get answers here to explain the significance of that critical value of 9. Okay? Across the top, we are going to put 3 times 6 minus x and 2 times 9 minus x to the half. I know you know that the derivative is not the product of those things. But if what we're trying to find is whether the derivative is positive or negative, when you divide these factors or multiply them, the rules are the same. If the top is negative and the bottom is negative, the derivative will be positive. Always, 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 always positive. Why? Because this half means the principal square root. It's got nothing necessarily to do with the domain. If I had a factor of root anything, everywhere that thing is defined, it will be positive. This crosses over, so to speak, at 6, but it goes from positive to negative because it's 6 minus x. Graphically, it's like a line that points down, crossing through 6. Which means the derivative is positive, then the derivative is negative, which means the function is increasing and then decreasing. If you didn't include that 9, or if you, no, maybe that's not what I want to say. Is the derivative defined at 9? Look at your derivative. It's just peeking at the top of the screen here. Is this derivative defined at 9? No. Let me reveal to you what this graph is going to look like. We can check it on a graphing calculator, but I'm pretty confident I know what it's going to look like. It's going to look like that. It's not parabolic. It's got a kind of a weird shape, I think. Why is the derivative equal to 0 here? Because the slope is 0. Increasing before that point, decreasing after. Why is the derivative not defined here? Well, because you can't divide by 0, but it's not defined graphically because that's an endpoint. A derivative is the slope of the tangent, which is a limit which has to exist on both sides. So this is all, there's a lot hitting you today, but this is all going to come together. We might as well take a quick peek at what this looks like. Was it x root 9 minus x? Okay. Your graphing calculators, I don't know how the newer ones will fare, but around these points that are end points or kind of cusps, that's not really a cusp, they don't do a very good job. What do I want to do? Let's go, I'll go start off with Zoom Standard. So this is what I mean. The function comes up and then goes down, and it leaves a little gap there, and it's because it's getting quite steep, but that's what the function looks like. If you were to sketch this on paper, of course, you'd put an arrow on this, and you'd put a point there. And the coordinates of that point will be 6 comma something. So it's really interesting. What you are learning today is how to find out where maxima and minima are for any function, if you can differentiate it. Okay. So that's it. I hope that made sense. On page 170, questions 1 through 4 are relating to this whole increasing and decreasing thing. And probably none of these questions will talk about max or min. But critical value of x, critical value of x, critical value of x, critical value of x. Because the derivative is undefined at these 2 points. By the way, there should be arrows on the ends of these, right? Anyway, get to work on those. You got about 15 minutes to practice some of these for tomorrow. Of course.